So now I decided, since I had the oscilloscope out, it's not even done charging, which is weird. Okay, looks like, no, it is still charging. But any case, it's taking a lot more charge than I thought it would be. We have the oscilloscope. It's actually measuring 2 voltages right now, but you only see the green line right there. So that is the trim pot that we are measuring. There you can see the voltage move. So you can see when I lower the trim pot voltage down to 0 volts, we are actually working with a 9 volt supply, because that's what I used in an earlier circuit. We have all the way down to 0, and we can go well above 5 volts because we got 9 volt supply there. But now you're going to see something interesting at the 7 volt mark. So I'm going to actually zoom in so we can see this. So you're going to see at about 7 volts, that's where the output of the op amp levels off right there. So the output can't get all the way to the positive supply. So that is why it is a single supply op amp. And when we had a load, you know, you can see there that the LED is not lit right now. So technically there's no load anymore. There's not enough voltage to light the LED. If we had current going the other way, because that's what I do with the blue LED a lot, then it would need current, and I think we'd stop at about 1 volt. But we can drop down, going that way, to 0 volts with both of them. And it's not all the way down. That should be 0 volts right there. So I'm going to remove the green jumper, and okay, we got static. That didn't work out too well. I'll go to the positive supply. There we go. That'll get it out of the way. Okay, we got the green out of the way. All that scramble was my body, by the way. So we have the green out of the way. There you can see the orange at 0 volts. So even though it's not measuring it right now, we do still have about 0 volts right there at the output. And so I mentioned my body. I'm going to grab the orange one now. So that's picking up like stray signals there. That's why it's going crazy. And now it's about 60 hertz right there. So about 60 times a second, the voltage is going up and down like that. So it's just the electricity in the house right there. It's bombarding me with the electromagnetic fields, which really don't do anything unless you're measuring your voltage with something sensitive, your body's voltage. So we're back to the output. Yeah, that's about all I can think of. I think I covered everything that there is to know. This is wired, this op amp, so now their voltages are equal, as a voltage follower. That's the circuit that you wire if you want the output voltage to be the same as your input. And why would you do that? Because this trim pot has a lot of resistance in it. You can see we're halfway right there. So if we were trying to set half of the supply voltage across the LED and its current limiting resistor, we would also have, it's a 10K trim pot there. They come in different values. We would have 5,000 ohms of resistance coming from the positive supply before it got there. So we would not have half of the supply voltage of 4.5 volts, even if I set this halfway. It's almost impossible to, set a voltage across the load with the trim pot because of its resistance. The op amp, on the other hand, and since we're not looking at the oscilloscope, we'll get these out of the way. You can see that the output has a little jumper there going to the inverting input, and the output always wants to be more like the non-inverting input, or trim pot there, than the inverting input. And thus, if the non-inverting input has a higher voltage than the inverting input, the output voltage goes up. If it's lower than the inverting input, then the output voltage goes down. Ultimately, when you got this feedback right there, it's called negative feedback. It just instantly makes the output the same voltage as the non-inverting input. Once they have an equal voltage, the output voltage holds the same. So it sucks it right to the equal voltage that we have at the non-inverting input. So hopefully that makes sense. You can see this is the alligator clips where we clip to ground, the negative supply in the circuit. And then the probes, we have a little hook. If you squeeze this down, a little hook comes out. And I can hook it to wires or the leads there. And if I want to try to make sure I don't short something, I can tack that into the board. So that's with either of these. This is a, I think 2 channels is all I got with this oscilloscope. But we're measuring 2 voltages, so it's 2 channels, the 2 probes. Each one has its own channel right there. We can change how fast this is scrolling across, and this is roll. I can't remember what the other name is, but if you're looking at really rapid voltage changes, then it kind of takes a picture every once in a while, but you see a certain amount of time on the screen where the waveform had changed, if you got things set up right. Otherwise, if you don't have it set to read fast enough, you might see a whole bunch of stuff, or you might just kind of see like a straight line, but it's actually moving, but your little snapshot was too quick. So in any case, not a detailed oscilloscope video, but I kind of assumed most people watching this video aren't familiar with them, so I thought I would mention that. Really cool unit to have, oscilloscope, especially if you have changing voltages like we did in this video. I can change it all over the place with the trim pot. So rambled on long enough. Thanks for watching. Make sure you check out one of the other videos I posted on the screen, and check out the links down below. They all help out a lot. I'll see ya in the next video.